Welcome back. We now broach a new module, one dealing with classic clustering techniques, and it consists of 3 lectures, 3 sets of slides. In this first one, we consider Kmeans, one of the most often used clustering methods. And what I'm going to do is start with a brief review of the principles behind clustering, which is really a very important form of unsupervised learning, as it's called in machine learning context. Then go over the Kmeans algorithm and how to interpret it and apply it, and close with some words on what we do with the actual clusters that we obtain. What are they for? So, as I mentioned, the core principle in clustering is so-called unsupervised learning. What that means is that there is no model. We let the data speak for themselves. And so whatever grouping comes up from the data is not predetermined by some kind of model. For example, there's other clustering techniques such as mixed modeling that are based on a distributional assumption, typically a Gaussian assumption, and so there is more structure in that. And so there is something called semi-supervised learning, and then supervised learning is really about prediction, and so fitting a model and finding a good prediction. So this is very different. This is really essentially about grouping similar observations. And similar will be defined in a number of different ways, as we'll see in a second. So what we're trying to do is group observations together that maximize the similarity within the group. So they are as alike as possible within the group. And then we want the groups to be as dissimilar as possible. So we minimize the between group similarity, or more intuitively, we maximize the between group dissimilarity. So we want to make sure that inside the group they are as similar as possible, and that the groups themselves are as different as possible. And then the other principle is that each observation belongs to one and only one cluster, one and only one group. So it's exhaustive. Every observation is assigned to a cluster, and exclusive. You cannot belong to more than one cluster. There is a form of clustering called fuzzy clustering, where there is a degree of cluster membership, but we won't go into that. So in the methods we'll consider in the next 3 lectures, we're really about assigning each observation to one of k groups, k clusters, such that they are as alike as possible within each group, and the groups are as different from each other as possible. So, whereas before in the previous module, we talked about dimension reduction, and it was really about the dimension in the variable dimension, so reducing the dimension of the attribute space. Here there's also a form of dimension reduction, but it's in the observational dimension. So what we're doing here is starting with a large number of observations, and in a sense we're simplifying that to smaller observations, smaller groups of observations, where maybe the group mean then becomes representative for all the observations in the same group. In the similar way of thinking as we had before when we reduced, say, the original variables to a smaller number of principal components. It's a reduction in the dimension, but here it is in the dimension of the observations. This is a very large topic with a very large literature approached from statistics, from machine learning or computer science, from database theory, from operations research, and there's many different issues involved. One is, of course, so far I've mentioned similarity and dissimilarity. How do we operationalize that? And we can use different distance measures, Euclidean distance, Manhattan distance. We've already seen this before in multidimensional scaling, for example. We can use correlation measures as measures of similarity, although correlation only measures linear similarity, and there's several others as well. So that's one big decision to make, is what is our criterion to define similarity. Another equally big decision to make is how many clusters do we want? And in many methods, we have to predetermine the number of clusters. In others, we don't. But how do we decide which is the right number of clusters? Should it be 4? Should it be 10? So there's many rules of thumb. There's also some more formal measures. So that is one important aspect of the cluster analysis. And then another aspect of the cluster analysis, which is related to this, is how do we measure how good a cluster is? Because, say, if we want to choose between a cluster analysis with 4 clusters and one with 5 clusters, how do we compare the two? What are the proper criteria to look at? And so that's another choice that we need to make. This is very hard to do. This is a computationally very challenging problem. It is what is called NP-hard. It's combinatorial. You can think of it as being essentially very simple. You have n observations and you have to put them in k groups. So you might say, why don't we just enumerate all the possibilities? Well, all the possibilities amount to k to the power n, where n is the number of observations and k is the number of groups, the number of clusters. And even with k as small as 4 and 85, which is the number of observations in our Gary example, k to the power n is something of the order of 10 to the 51st power. So it's combinatorial, it's tough. There are typically, in almost all the cases, no analytical solutions. So we have to use heuristics. Heuristics are algorithms. An algorithm is a series of steps to get to a solution. And heuristics are algorithms that seem reasonable, but there's typically no guarantee of finding the best solution. There is no guarantee of finding a global optimum. So we'll find an optimum, but it could be local. I mean, think of a mountain range with 2 peaks, and one peak is higher than the other. As you climb the first peak and you are on top, you think you're there. You've found the optimum, but then in fact, there is this other peak, which is actually higher. So you're not in the highest peak. And so designing methods that avoid to get trapped in these local peaks, so to speak, these local optima, is one of the challenges of heuristics for clustering algorithms. And we'll see some examples of that later on as well. The clustering methods, or if you wish, this aspect of unsupervised learning, boils down to 2 main approaches. One is called partitioning clustering, the other one hierarchical clustering. And there's really no best among the two. They're both good at certain things. They have pros and cons. And one of the things we'll do in the discussion that follows is to highlight some of the aspects where one may be more suitable than the other. So partitioning clustering starts with a random assignment. So we have our n observations. We randomly assign them into k groups. And then we carry out steps, iterations. We iteratively improve the allocation. That is typically carried out by what is referred to as a iterative greedy algorithm. Greedy because you look for the best improvement. And so you move on and on and on until the improvement is no longer significant, and then you stop. And as I mentioned, you stop, but you're not guaranteed to be in a global optimum. You're in a local optimum. One of the important characteristics of partitioning methods is that you have to pre-specify the number of clusters. So as in, for example, Kmeans, which is one of the partitioning methods, you have to specify k. K is 5, k is 10, and then you carry out the analysis. Hierarchical clustering uses a different principle. It basically works through all the data, either from the bottom up, that is called agglomerative clustering, or from the top down, that is called divisive clustering. In agglomerative clustering, you start from the bottom, where initially every observation is its own cluster. So if we have n observations, we start with n clusters. And then we put the two that are closest together in a new cluster. So now we have n minus 1 clusters. And we move up the tree until all the observations are one single cluster. And then we have to decide at what point we cut the tree, as we'll see in the next lecture, to determine the number of clusters. Divisive hierarchical clustering works the other way. It starts with all the observations being one cluster and then splits that into two groups that are the most different from each other, and then keeps splitting and splitting and splitting until at the end, again, every observation is its own cluster. So the approach, it's also iterative. At each step, the number of clusters is either one less in the agglomerative approach or one more in the divisive approach. And so once you have done this grouping or cutting of observations, then you decide the number of clusters. So that's a major difference between partitioning methods and hierarchical methods. Okay, K-means. K-means is a way to allocate each observation I to a given cluster H. So we have K clusters, H equal 1 through K, and each observation has this encoder C that says observation I has to be in cluster H. Okay, that's just a way to formalize this notion. And we want to find an encoder, which is essentially a way to assign observations to clusters in function of this T notion, which is the sum of all the pairwise differences, all the pairwise distances between observations. So we have n observations, so we have n square pairwise distances. The distances to yourself are 0, so we don't have to worry about those. But distances are symmetric, so we divide by 2, or we don't. It doesn't really matter. If we don't divide by 2, we count everything twice. So this is what is driving, this is really the essence of the objective, is we measure the sum of total differences, and then we're going to see how the sum splits itself, so to speak, between the distances in each cluster and the distances between the clusters. And this distinction between within and between dissimilarity is critical to the cluster approach. So for each cluster, to think about this a little more concretely, consider a given cluster. So we have all the observations I that are part of this cluster H. And now we're computing, just for the observations in the cluster, this measure of all the pairwise distances. So we sum over all the I in the clusters, and we compute the distances from the observations in the cluster to all the other observations. So all the other observations, all the J, can be categorized into two groups. One group that is in the cluster, and then one group that is not in the cluster. So this is the principle. We take all the distances between the members of a cluster and everything else, and that splits itself into the distances to the other members of the cluster, and then the distances to those observations that are not in the cluster. So now we can do this for each cluster. So we sum here over all the clusters from 1 to k, this same expression. This expression is the exact same thing. And because we sum over all the clusters, we are actually summing over all the I. So we're doing this part for the I in each cluster, and then we sum all the clusters, which makes us sum all the origins. And this split of the total sum of all the pairwise distances or pairwise dissimilarities is between the what we call the within dissimilarity and the between dissimilarity. And our objective, as we've already stated, is to minimize the within similarity or maximize the between similarity. So if this one goes down, then this one goes up. There's no other way, because the sum of all the pairwise distances is not changed by allocating an observation to a cluster. These are still all the same observations, and since we sum over all the clusters, we sum over all the origins, and we sum over all the destinations. So the total doesn't change. The split between within and between is what changes as a function of our encoder, which allocates particular I observations to particular clusters H. That's what's going on. In Kmeans, the objective function is not the distance or the dissimilarity itself, but for a number of reasons, it's the squared Euclidean distance. And we're already familiar with the Euclidean distance from our discussion of multidimensional scaling. And just to repeat it, the distance square is the sum over all the variables. These are all the variables of the pairwise difference squared, right? So this is the multivariate dissimilarity between observations I and J. And we want to find an encoding C of I, meaning an allocation of each observation I to a given cluster that minimizes the within dissimilarity. And the within dissimilarity is the sum over all the clusters of all the origins in the clusters, and then all the destinations within the cluster of the squared distances. And we can divide it by 2 or not to find a minimum. That's not going to make any difference. And now there is a very important property which is similar in nature and it uses the same kind of algebra as what we had earlier when we discussed multidimensional scaling, when we found that the doubly adjusted squared distances were the same as the Gram matrix, the XX prime matrix. So similar algebra, and the details are in the lab notes, gives us the result that the minimum of these squared Euclidean distances is the same as the minimum of the deviations from the cluster mean of all the observations in the cluster. So we're replacing the origin destination notion that we have here by an origin only notion. Obviously, as the encoder changes, the mean of each cluster will change as well. So this is not making it any easier, but it just allows us to interpret these this notion of minimizing within dissimilarity as minimizing a concept of variance, if you wish. This square difference from the mean is a notion of variance within the cluster. So we try to minimize the variance within the cluster. That's the objective function. The way we go about this is by means of what is called iterative relocation. And the original algorithm is called Lloyd's algorithm. The way it works is you start with an initial random solution. So how does this work? Let's say we have a cluster with k equal 5. We pick 5 starting points, and then we allocate all the observations to one of these chi K groups, and then one of these 5 groups. And then after that, we improve the solution by so-called iterative greedy descent. So descent means we descend down the within sum squares, so that is being minimized. And we have a way to go about this that guarantees that at each step the within sum squares is smaller, and we do this until there's no more improvement. But as I mentioned before, this yields a local optimum, but there's no guarantee of having a global optimum. So that's one of the challenges with these clustering algorithms. And this is something that may throw you for a loop once you start doing more of these cluster analyses, is that they all give slightly different results. And then in the end, you have to make a decision which of these different results is most reasonable for your particular research question. So this is just part of the clustering routine. So let me go through a simple toy example. We have our 7 points. The center, so the overall mean of the 7 points, is this orange dot, just to give you an idea. So the orange dot is itself not part of the clustering routine. So how do we go about this? Let's say we keep it simple and we want k equal 2. We need to start with 2 random starting points and then assign the other points to them. The way Kmeans does this is start up here in the upper left. So randomly, quote unquote, I picked 4 and 7 as the starting points. And now we have to allocate all the others in Kmeans to the closest starting point. So all the dark blue ones are allocated to 4 as a starting grouping, and the dark green one is allocated to 7. So now we have this situation. We have these 5 dark blue ones and these 2 dark green ones. And each of these now gets a new center. Remember, the original center was somewhere here. Now we have a mean for each of the subgroups. Remember, we're trying to minimize the square deviations from the mean. So we compute the new mean for each group, and then we allocate the points to the closest center. And so in our particular example, 5 is actually closer to the green center than to the blue center. So we now move 5 into the green cluster and recompute the centers. So the new center for the green cluster drops a little bit. For the blue cluster, it also moves away a little bit. And now 4, so all of these stay allocated to this center, and the green ones also stay allocated to the center. The only one that moves is 5. So in the next step, we have to look at the new centers, the new means, and now 4 is closer to the green center than to the blue center. So we move 4 from blue to green. And then we have new centers. At this point, there is no more movement. Every one in the group is allocated to the closest center, so we're done. This is where the algorithm stops. And at this point, you can see the separation between the two regions is kind of like a Thiessen polygon, if you remember that, between the centers of the clusters. So K-means with physical distance, as in this example, boils down to a separation of the observations into regions determined by Thiessen polygons. We'll revisit that later. But in essence, the K-means start with random seeds, as many as K, and then recompute the center of each cluster by allocating the points to the observations to their closest mean. And now in multivariate space, of course, you can't show it in two-dimensional graph anymore, but it's the same thing. You start with seeds, you find the observations in multi-attribute space that are the closest to them and assign them to those clusters. Then you recompute the mean for the new group and reassign to the closest mean, and keep doing this until it doesn't change anymore. That's the essence of Kmeans. The result is something like this. This is our Gary example again with the 6 variables, and k is 5. So we see 5 groups. 3 are fairly balanced. 1 is a little larger than the others, and 1 is a little smaller than the others. In the lab, we'll look more carefully at the characteristics of the different clusters. So this is what we get with a standard result. That's the kind of thing. So what are we interested in now? What are the characteristics of the clusters that matter for us? The cluster centers. Remember, the cluster centers are the mean of the observations that are assigned to the cluster. So for each of the variables that we involve in the clustering exercise, we can see what that mean is. Now, that mean in Kmeans is not typically an actual observation, but it is a representative observation. So we can compare the clusters in terms of their representative observations. And this is where the interpretation of the cluster comes into play, which is not always that straightforward. But let's say one variable is income and another variable is education. And cluster 1 has a very high mean for income and education, and cluster 2 has a very low mean for income and education. Then you can start verbalizing the structure of the clusters or the characteristics of the clusters in terms of those mean variables of the representative point. Then the fit of the cluster is measured by the sum of squares. That's where the sum of squares comes in really handy. So we start with the total sum of squares, which doesn't change. That's our t from the beginning. The t doesn't change. What changes is the split between the w and the b, between the within sum of squares and the between sum of squares. So for each cluster, we can compute the within sum of squares, and we can add them up and get the total within sum of squares. We can also get the total between sum of squares. The sum of these two is always the total sum of squares. So if you compute one, you can get the other one just by subtracting it from the total. And then what we're interested in is the ratio of between sum of squares to total sum of squares. We try to maximize that. We could equivalently take the ratio of within sum of squares to total sum of squares, and that we would like to minimize. So in GeoDa, this is the typical result of a K-means clustering. So at the top, it gives you the method that is used, the number of clusters, the initialization method. I'll talk about that in a few minutes. So it's not the default actually, but what I explained so far is a random start, so randomly pick k starting points. We repeat this 150 times and then pick the best one. And then the maximum iterations, so if we haven't found a point where there's no more improvement, then we stop after 1,000 iterations. The cluster centers for each of the variables are given here. And for example, you see that the cluster center for the crime against persons, remember the variables are flipped, so higher value is lower crime. C3 has much lower crime than C2, for example. And so with a little bit of imagination, sometimes with a lot of imagination, you can look at these means and interpret the clusters in terms of their profile on the different variables. And then in the bottom, we have the analysis of the fit of the sum of squares. We have the total sum of squares for each cluster. We have the within sum of squares. Obviously, the sum of all of this is this value. The complement, the difference between 504 and 253 is this value, and then the ratio of between two total sum of squares is 0.497. By the way, that's not that great a result, but it's just here for illustration purposes. Okay, how do we pick k? Very similar to what we did in the principal component analysis. We can look at k from from 2 and on, and look at how the within sum of squares decreases, or the ratio of between two total increases, in the sense that, just like with the scree plot for principal components, we can draw an elbow plot, and we're looking for an elbow. We're looking for a point where the decrease kind of levels off, or the increase levels off. So we want to find a kink in the elbow plot, and that is the best k. There's also other more quantitative measures to find the best k, but they tend to involve a lot of additional computation. And in any way, it's not that clear. They make some assumptions that are not necessarily that useful. So this illustrates the logic. For our Gary example, we start with a cluster of 2. Within sum of squares is 383. When we go from 2 to 3, it drops by 57. Then from 3 to 4, it drops by 40. So you see the drop here is smaller and smaller until it kind of, it doesn't flatten. Flatten would mean the drop is 0, but the drop is much smaller. So it's very hard to tell where you would cut. I would probably cut around 7, where you see a big difference in the improvement. And similarly, you can look at the ratio here, where, of course, it goes up by 0.11 first, 0.8, 6, 5, 5, 4, and then here 2, 2, 2, 2, 2. So it's the same thing. So this elbow plot, this is a very similar comment that I made in the discussion of principal components. In principle, this is great. In the textbooks, they tend to look great. In practice, it's not always that easy. For example, in our Gary case with the 6 variables, there isn't really a flat part here or here. I mean, it still increases. It doesn't really flatten out. I've seen other examples where it's much clearer, and there is like a clear kink at, say, 6 or 7, and then it's flat, pretty much flat after that. That's what you want. That's not necessarily what you get in actual applications. So far, the classic approach was to pick k seeds at random and then allocate the observations to the closest seed, and then start from there. And you do this many times. So as it turns out, this is a very important, this has a very large effect on the ultimate solution. So where you start affects very much where you end up. So this has been a kind of a problem of the Kmeans approach, in that if you start from a different random seed, you get a different end result. So depending on where you start, you get different results. And one way to deal with this, and with fairly small problems and a fairly fast machine, you just increase the number of initial starting points. And for each of these, you compute the within sum of squares, and then you pick the one with the best within sum of squares, and then start the iterative greedy descent from that point. So it's always with k clusters, you pick k seeds, and then you allocate the observations to those k seeds. In the standard classic K-means, the k seeds are uniform random numbers. They're just randomly picked with a uniform distribution. So since the initial point of departure is so critical, there's been a lot of research on how to improve that. And one method that has received quite a bit of acceptance is called Kmeans++. And it's due to Arthur and Vasil Vitsky. And the idea is actually very clever. It's saying, okay, let's pick the first seed randomly. But then let's not take the second seed randomly, because really what we want is we want these seeds to be as far from each other as possible. So rather than taking the second seed randomly, we're going to compute a distribution of the likelihood that the second seed is taken, and we make that distribution a function of the distance to the existing seed or existing seeds. So if there's only one seed, then it's very easy. If there's two, then we have to take all these other distances into account. So basically, for every point that hasn't been picked yet, so we pick k points, after we pick one, there's n minus 1 points left that we could pick as the second seed. For all of these points, we compute a probability as a function of the square distance from that point to the existing seed, or later on to the closest seed that it's to. And then these probabilities since the sum in the denominator is the sum of all the numerators, so even if you have different c's taken into account, they reappear in the denominator, so it remains a probability, and that is between 0 and 1, and it sums to 1. So these probabilities are then used in the second draw. So it's no longer equal chance for any point to be picked, but the chances have been weighed, in a sense, as a function of the distance to the existing seeds, in the sense that points that are further away from the existing seeds are favored. So they get a higher probability of being picked. So then this is Kmeans plus plus. You get your K seeds, you assign the observations, and you compute the within sum square. And again, you can do this multiple times and pick the best one. So that's Kmeans plus plus. And as it turns out, in our case, the result is not that different. In fact, the overall result is just slightly worse than in the randomization. This highlights one important element in cluster analysis, and I will likely repeat this several times, is the importance of sensitivity analysis. Since the end result depends to a large extent on where you start, it's very important to get a sense of how important that really is. And so it behooves one to try different starting points and assess whether the results are more or less the same, with slightly differences in these center means, the representative means, and maybe one is a little better than the other in terms of the overall fit, but in essence, they're picking up the same patterns, which is really what it is about, versus situations where it just completely flips around. Then you have to get very nervous and start thinking about maybe K is wrong, or maybe I need to run even larger number of starting points, and so on. Okay, finally, to conclude, what do we do with these clusters? And first of all, as I've already mentioned, we try to interpret the groups through cluster averages. For example, in marketing, you're maybe familiar with the notion of a prism, and there's several other different commercial solutions that essentially divvy up the demographics of the market into different subgroups, millennials, retirees, these kinds of groups that are not just based on age alone, but they're based on occupation, income, savings, value of their house, and so on and so on. All these different variables are thrown into a big pot, and then out come these clusters that are based on the averages for each cluster center, get fancy interpretations. As I said, this is more an art than a science, but is the fun part, is to give the names to the clusters. Another more statistical use is to use the cluster variable as a categorical variable to assess spatial heterogeneity. And then the cluster membership becomes something that can be used in conditional plots or in analysis of variance, or in spatial regimes in regression analysis, and so on. And then finally, we can also, and this is often, we'll encounter that when we focus more on spatially constrained clusters, but it's often important to go back to this original motivation of dimension reduction in the observational dimension. So we actually reduce the number of observations to the clusters and then use some kind of cluster average or cluster aggregate as the variables in our analysis. And for example, this is a conditional box plot that's available in GeoDa. So for each, this variable is literacy. There are 5 clusters. Each cluster has a categorical tag. I mean, these numbers don't mean anything. 5 is not more than 4. It could be A, B, C, D, E. They're pure categories. They're different clusters. But for each of the clusters, we can plot the distribution of the variable of interest. And for example, we see that the median, this orange line, is much lower in cluster 1 than in cluster 2. 2 and 3 are about the same, but then 4 and 5 are again much lower. So this allows us to carry out tests on difference in the median, tests on difference in the mean, analysis of variance, and so on, looking for structural differences following the categories as defined by the clusters. So that's one important use of the cluster results. A second important use, as I mentioned, is the aggregation. So this will be more relevant when we impose spatial constraints, because here we see that the regions, so to speak, are not connected. So they're parts all over the place. But still, we can carry out an aggregation in the GIS speak. This is called a dissolve operation, where we merge all the original units into one larger unit following the cluster category. And then we can also cluster on the results of a dimension reduction. In fact, oftentimes this is more practical than dealing with a very large number of observations. I mean, that's the whole point of dimension reduction. So instead of, say, carrying out a cluster analysis on 50 variables, you reduce the 50 variables into 5 principal components and then carry out the cluster analysis on the 5 principal components. If these principal components capture much of the variance, of the original variance among the variables, then we're in good shape and we will tend to find the same or very similar patterns as if we did it for all the variables. Now, if we can do it for all the variables, fine, but there are contexts where the number of variables is just too large, and so that's the whole point of dimension reduction. That's the whole point of principal components. So we do this sometimes to facilitate the interpretation, mostly for computational efficiency. So we can take principal components and carry out the analysis. And now I want you to watch these next 2 graphs very carefully and think about it for a second. So in the first analysis, I have taken the 2 first principal components and carry out a Kmeans analysis on these components. What you see in the left is the location of every observation on the 2 principal components, and we observe that, in fact, Kmeans carries out a regionalization in attribute space, which is exactly what we want. So these are points in attribute space that are close together, and they are grouped in a similar cluster. Now, these clusters are all over the place. We'll address that later when we do the spatially constrained part. So 2 principal components from our 6 variables, and we get these clusters. Now, we can do the same with multidimensional scaling. If you pay close attention, first look at the map. The map doesn't change at all. Now look at the graph. The graph it seems different, but in fact is just flipped. Look at the orange points up on top here, and these are the orange point on the bottom. Now, why is that? Why do you think that is? Remember that classic multidimensional scaling is nothing but using the first principal components. So these are in essence the same points in the same space. Whether you plot the points in the first two principal components, or you plot the points in the space of the first two dimensions in the multidimensional scaling using classic metric scaling, which is the square root of the eigenvalue times the eigenvector, you get the same relative position. So the clustering on the locations in the multidimensional space is the same result as the clustering on the principal components. Both of these illustrate how you can, in a sense, simplify the clustering process. And then if you look at the clustering result, it's actually not that different from the original result. So that's what you want. So this concludes the first of 3 lectures devoted to classic clustering. Kmeans is a partitioning method. It has an algorithm, a greedy heuristic, iterative, greedy, steep descent, so it's always better. The key criterion is the within sum of squares. We saw how the distances can be equivalent to the square difference from the mean in each cluster. And then we saw how the initial point, the point of departure, is very important. So we have classic k-means with a random allocation, and then k-means plus plus, which imposes a logic in the initial points. The technical details are given in the lab notes. So next, we'll continue with hierarchical clustering. See you then.